Attack bagels, activate. Practice problem number 70 of conservation of energy. And we're going to be using conservative forces here, so we don't have to worry about losing any energy to work. And in this problem, we've got a slightly different example here. Previously, what we've been doing, we've been looking at one object pretty much. A basketball moving, or a person moving, whatever. In this scenario, we're going to have multiple objects. Same ideas apply for the conservation of energy. Whatever mechanical energy you have initially, this must be the mechanical energy you have in the final state for conservative forces. And we are going to assume that whatever collision we have here will be fully conservative and we're not going to lose any energy. Okay? But what we have in this scenario are two blocks. They each have the same mass, 0.25 kilograms. And they can slide without friction on a horizontal surface. Note, there's no friction, so these are all conservative forces, and we're on a horizontal surface. This immediately clues us in to the fact that we don't need to care about the gravitational potential energy. We're not going up or down at all, so that MGH that we've normally used, we don't care about it. We don't even need to put it. Initially, block 1 is in motion at some speed, 1.2 meters per second. Block 2 is at rest. Let's just doodle that real quick. Here's block 1. It's got a velocity of 1.2 meters per second. I'll call that 1I. And block 2 here is at 0. It's not moving. When these blocks collide, when block 1 hits block 2, a spring bumper on block 1 is compressed. So there's a little spring right here on block 1 that is being compressed. Okay? So right there's a little spring. It's being compressed. When this spring is at its maximum compression, the two blocks are going to move at the same speed. So block 1 and block 2, when this spring is at its maximum compression, both of these blocks are going to move with some final velocity of 0.6 meters per second. This max compression of the spring is 1.6 centimeters, or 1.8 centimeters. So that's 0.018 meters. That's going to be the max compression of the spring. What we're trying to solve for in this problem is the force constant of the spring, or that spring constant. We're looking for K. How strong is that spring? So if we're looking for the spring constant here, let's use our conservation of energy to set this up. Now, normally when we do this, we would only think about kinetic energy for one object. But we have two kinetic energies here. When we're actually thinking about this, we're thinking about the kinetic energy initially of the first object, plus the kinetic energy initially of the second object, plus any of the potentials we have for object 1 and object 2. Luckily for us, in this scenario, while our first object has some kinetic energy because it is moving, our second object is at a velocity of 0. It's at rest in the beginning. So its kinetic energy goes away because it never had any to begin with. Furthermore, when we think about the potentials, we've already mentioned that the MGH, that gravitational potential energy for both of these objects, isn't changing. We're on a horizontal surface. So we don't care about the potential due to gravity. And in the beginning of this, the spring we have here, it's not compressed at all. So we actually it doesn't have a potential either. It doesn't have a potential energy either. It's not compressed or stretched at all. It's doing nothing. So in the beginning, we actually don't care about any of the potentials. So the only energy we have initially is the kinetic energy of this first object. We have a 1/2 multiplied by its mass, so that's 0.25 kilograms, times its initial velocity, 1.2 meters per second, squared. That's the only energy we have at the start of this problem. After they've collided, that spring has become compressed. They're now moving at new speeds. Now we have kinetic energies for both objects. We've got kinetic energies for the first object. We've got kinetic energies for the second object. And that spring is compressed in there. There's a spring or an elastic potential energy. If we take a look at these kinetic energies here, we're going to have 1/2 times the mass of 0.25 times the final velocity, which we know is 0.6 squared. And the second object, the second block, has that same value. So 1/2, 0.25, 0.6 squared. If you wanted to, you could have combined these masses because the objects are moving together at this specific moment. You couldn't combine the masses in general if they had different speeds, but in this case you could. I don't like to do that. I like to keep everything separate so I know that I have both of my objects there. But if you want to do what you want to do, you're still doing the math. Okay, you can see that these are completely like terms. They're just going to go together. Now we also have to put our spring in here. Our spring has a value of 1/2 k, which is what we're looking for, times x squared. And that x is the compression of the spring, which at maximum is 0.018 meters. Don't forget that square up top. Everybody always forgets that. Deals them a lot of harm on these problems. And with that set up, that long equation, the physics is done. There's no more physics to do in this problem. The physics is over. Everything from here on out is just cranking numbers through on a calculator again. That's it. As always, please be careful whenever you're entering numbers into the calculator. I always love to start with my squares first and then crunch things together to get numbers on things. And another interesting thing about this problem is, unlike previous examples that have had mass in every term, and we've been able to kind of divide out the mass, in this example, we can't do that. The spring energy here, or that elastic potential energy, doesn't have a mass in it, so we cannot eliminate the masses here. Okay? So let's start churning out numbers and see what happens. 1.2 squared is 1.44 times 0.25 divided by 2. We get 0.18. And that will be joules if you want to include units. Over here, we've got 0.6 squared, so that's 0.36, times 0.25, so a quarter of that's 0.09. And then divide by 2, we're going to get 0.045. So this is 0.045. This is 0.045 as well, because it's the exact same. And if we put them together, we're going to get 0.09. And that's going to be added to our 1/2 k, and this is going to be 0.018 squared. At this point, we're still just doing algebra. Everything on this spring is tied together, so I actually need to get rid of the 0.09 first. So I'm going to subtract 0.09 from each side to get rid of it. 0.18 minus 0.09 is 0.09. So we get 0.09 on this side. That unit is still joules for energy. And then on the right side, I'm going to finally square the 0.018 and then multiply it by 1/2 or divide by 2, however you like to think about that. So 0.018 squared gives me a very small number, 0.000324, or 3.24 times 10 to the negative 4. And then when I divide that by 2, or multiply by 1/2, I get the quantity 1.62 times 10 to the minus 4. That's multiplied by our spring constant there. And at this point, to get k, I just need to divide that out. Remember, if you're on your calculator, whenever we type in that times 10 to the minus 4, it's best to write this out. Like if I were to type everything in, every single number, I would type in 0.09 divided by, and then because I'm paranoid, I always put a parenthesis, 1.62 e minus 4. This is how we write that on our calculators, but that would give us our value of k. When we do this, we get a value for k of 555.55555. You get the idea. And that's our final answer. Once again, we've seen that our physics ends up here with the picture and the equation. Everything else is just churning out some algebra in order to solve our final answer. Trust that your setup is correct. Most of the mistakes student makes as they're going through this deal with the algebra as you're still learning your mathematics and getting better at it. Most of the times students set up the physics correctly, and it's that algebra where they make a mistake. So don't worry about it if you're struggling with that algebra. Seek out help from your math teacher, seek out help from your friends on how they're doing algebra, but trust that you're probably doing the physics correctly as long as you're drawing that picture and setting up that big equation. So this problem is now finished. In our next little videos, we're going to be modifying these a little bit. These conservation of energy problems have thus far only been using conservative forces, so we've always had all of our energy. In our next examples, we're going to see what happens whenever friction becomes involved. How does friction slow things down? Where does that energy go? And how can we still use our idea of conservation of energy even when we're losing some of it due to this friction? But until then, this problem's finished. Until next time, adios, and take it easy.